Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. This week in astronomy, NASA's SPHEREx, tracking objects through sound and blazing light from cosmic darkness. NASA's SPHEREx begins mapping the invisible universe. NASA's SPHEREx mission has officially begun its groundbreaking scientific observations, initiating an ambitious effort to map the entire sky in unprecedented detail. Launched on March 11, the spacecraft spent the first 6 weeks in space undergoing a series of checkouts, calibrations, and system verifications. These preparations ensured that SPHEREx, a space-based observatory designed to observe an infrared light invisible to the human eye, would be ready to fulfill its mission, to scan the cosmos in 102 different infrared wavelengths, producing a comprehensive 3D map of hundreds of millions of galaxies and providing new insights into the origins of the universe, the structure of galaxies, and the chemical building blocks of life in the Milky Way. As of May 1, SPHEREx has entered its phase of regular science operations. Over the next 2 years, it is scheduled to take approximately 3,600 images each day, culminating in a vast, digitally woven mosaic of the entire sky. This ambitious project will produce 4 complete sky maps during its primary mission, capturing cosmic features and structures in exquisite detail. SPHEREx orbits Earth about 14.5 times a day in a polar orbit, traveling from north to south and passing over both poles. This configuration allows it to systematically cover circular strips of the sky each day, and as Earth journeys around the Sun, SPHEREx's vantage point gradually shifts, enabling it to view the universe in every direction over the course of 6 months. The observatory gathers data using 6 infrared detectors that capture different wavelengths simultaneously, producing what are known as exposures, about 600 per day. Each exposure consists of 6 unique images, and together they represent a spectrum of invisible light that holds critical information about the distant objects being observed. Instead of traditional thrusters, SPHEREx adjusts its orientation using internal reaction wheels, allowing it to shift its entire body between exposures with precision and efficiency. One of the most striking features of SPHEREx is its ability to observe the sky in 102 colors of infrared light, a feat that has never been accomplished before. Unlike visible light, infrared light can pass through cosmic dust and reveal phenomena that would otherwise remain hidden. This capability allows SPHEREx to see into dusty regions of space, like the dense interstellar clouds where stars and planetary systems form. A striking early image from the telescope, taken at a wavelength of 3.29 microns, reveals a dusty cloud composed of molecules akin to soot or smoke, structures that are both visually stunning and scientifically valuable. SPHEREx uses a method called spectroscopy to analyze the light it collects. This technique splits light into its component wavelengths, similar to how a prism creates a rainbow. With spectroscopy, scientists can determine how far away a galaxy is, allowing them to assemble a 3-dimensional cosmic map instead of a flat 2-dimensional one. This depth of information helps researchers trace the expansion history of the universe and uncover the distribution of matter on the largest scales. One of the mission's most compelling goals is to shed light on cosmic inflation, a rapid expansion that occurred in the first fraction of a second after the Big Bang. During this phase, the universe expanded faster than the speed of light, going from subatomic to cosmological scales in an instant. This dramatic event left subtle imprints in the distribution of galaxies, and SPHEREx's vast sky maps are expected to reveal patterns that will help scientists decode this primordial mystery. By observing the largest scales of the modern universe, scientists hope to infer what happened at the smallest scales during its earliest moments, a poetic symmetry between the ancient and the vast. Beyond exploring the origins of the cosmos, SPHEREx also investigates the ingredients for life within our own galaxy. By analyzing the light from interstellar clouds, the mission aims to identify water and other essential compounds across a wide range of environments in the Milky Way. It is believed that the water found on Earth may have originated as frozen molecules on cosmic dust grains in the same interstellar cloud that birthed the Sun. SPHEREx will perform over 9 million such observations, allowing scientists to study how the chemistry of these materials changes with varying conditions and leading to a better understanding of the origins of planetary systems and life-friendly environments. SPHEREx does not operate in isolation. It is part of a broader strategy by NASA to understand the universe, complementing missions like the upcoming Nancy Grace Roman Space Telescope. Together, these observatories form a coordinated campaign to address some of the deepest questions in astrophysics, from the fundamental forces that shape the universe to the processes that foster life in its many corners. The mission represents more than a technological milestone. It's a fulfillment of over a decade of dedication from teams across NASA, academia, and industry. The instrument has performed exactly as hoped, meeting expectations with precision and opening the door to discoveries both anticipated and unforeseen. Scientists and engineers who have long worked toward this goal now watch as SPHEREx begins to deliver on its promise, to illuminate the hidden universe, transform our cosmic perspective, and perhaps uncover answers to some of the most profound questions about where we come from, what we are made of, and how the universe came to be as it is. Tracking space objects through sound. Space debris and meteoroids are constantly making their way toward Earth, creating a persistent and increasingly significant hazard as they streak through the atmosphere at high speeds. Among the tools scientists use to monitor these high-velocity entries are infrasound sensors, special instruments that detect extremely low-frequency sounds that human ears cannot hear. These sensors have become vital in detecting the acoustic signatures of bolides, which are meteoroids that explode or fragment dramatically in the sky, releasing large amounts of energy that ripple through the atmosphere as infrasound waves. However, tracking these events accurately involves more than just picking up their sound. A new study has demonstrated the importance of factoring in the object's trajectory, especially when it enters Earth's atmosphere at a shallow angle. Each year, Earth collects a surprising amount of material from space. Thousands of metric tons of space dust drift down from the cosmos, and around 50 tons of meteorites crash into the surface annually. Since the beginning of the space age, humanity has added to this influx with its own debris. Space junk, including rocket remnants, lost astronaut tools, and decommissioned satellites, hovers in low Earth orbit at astonishing speeds, often reaching up to 18,000 miles per hour. Occasionally, some of these objects return to Earth, their fiery descent creating a risk not only to technology and infrastructure but also to human life, however small the chance may be. When any space object re-enters the atmosphere, whether a natural meteoroid or a piece of artificial debris, scientists rush to track its trajectory. They need to determine not only when and where it will land, but also how it will travel through the atmosphere. Some may plunge directly downward, while others streak across the sky at shallow angles, skimming the atmosphere before coming to rest. Understanding this path is crucial for accurate predictions and, potentially, for issuing alerts or planning responses in the rare event of a dangerous impact. This challenge has drawn attention from researchers like Elizabeth Silber at Sandia National Laboratories, who is presenting her findings at the European Geosciences Union General Assembly. She focuses on how infrasound sensors detect bolides and how their readings are influenced by the angle at which these objects enter the atmosphere. Bolides are not static events, they are dynamic, fast-moving phenomena. As they barrel through the sky, they generate infrasound along their flight path, rather than from a single, stationary point. This creates a sonic footprint more like a sweeping boom than a single explosion. In cases where the bolide enters steeply, at angles greater than 60 degrees, the analysis of infrasound signals can reliably reconstruct the trajectory. But when these objects enter more horizontally, the signals become more complex and harder to interpret. The sound travels across longer distances and is picked up from multiple directions by different infrasound stations, increasing the uncertainty in determining exactly where the object was and where it might land. To dig deeper into this problem, Silber used data from a global network of infrasound sensors operated by the Comprehensive Test Ban Treaty Organization. Although this network is primarily designed to detect illicit nuclear tests, it also captures many other loud atmospheric events, from lightning to rocket launches. By focusing on bolide events, Silber was able to isolate the geometric elements of the infrasound data, specifically how the movement of the object affected the sound's propagation. Her findings stress that trajectory must be accounted for if scientists are to interpret the signals correctly, particularly for objects with flatter paths. This research underscores a larger point about planetary defense and the management of space debris. Infrasound sensors are an essential part of the global toolkit for tracking threats from above. However, their effectiveness depends on how well we understand and interpret the data they collect. If the direction and speed of an incoming object are not accurately reconstructed, it becomes much harder to predict its landing site or assess the risks. In short, knowing that something is coming is not enough. Scientists need to know how it's moving in order to respond effectively. This work not only advances our ability to monitor meteoroids but also has important implications for the safe management of space junk as our skies become increasingly crowded. Blazing light from cosmic darkness. Some of the brightest sources of light in the universe have their origins in some of the darkest places imaginable, the regions surrounding supermassive black holes at the centers of galaxies. These brilliant cosmic beacons, which we cannot see with the naked eye, emit immense amounts of energy across the electromagnetic spectrum. Satellites, particularly NASA's Fermi Gamma Ray Space Telescope, have revealed the astonishing number and variety of these luminous powerhouses since it began its mission in 2008. Despite their association with darkness, black holes help create some of the most powerful light shows in the universe. Fermi's Large Area Telescope, LAT, has cataloged thousands of high-energy sources. In just a single year of observation, data show hundreds of objects flaring and fading in gamma rays, captured in an animation where each object's brightness is indicated by the size of a glowing magenta circle. The sun's path is tracked too, represented by a yellow circle tracing its annual motion across the sky. Over 90% of these flashing gamma ray sources are what astronomers call blazars, a specific type of galaxy powered by supermassive black holes. Supermassive black holes are not rare, they lurk at the center of nearly every large galaxy, including our own Milky Way. These giants range in mass from hundreds of thousands to billions of times that of our Sun. While black holes themselves do not emit light, they are, after all, defined by their ability to trap even light. What surrounds them in active galaxies can shine intensely. In galaxies with active galactic nuclei, AGN, the black hole is surrounded by a dense, swirling cloud of gas and dust. As this material spirals inward, pulled by gravity, it forms a hot accretion disk. The friction and extreme gravitational forces at work heat the disk to incredible temperatures, causing it to emit radiation across a wide range of wavelengths, from radio waves to X-rays and gamma rays. This radiation is not the end of the story. In about 1 in 10 active galaxies, jets of particles are also formed and blasted outward from the region near the black hole. These jets travel at speeds approaching that of light and extend far beyond the galaxy itself. Scientists continue to investigate how black holes, with their overwhelming gravity that pulls everything inward, are able to power such outward-moving, high-energy jets. The process remains one of the more mysterious aspects of black hole physics. The appearance and classification of these active galaxies depend heavily on their orientation relative to Earth. When we see the jets side-on, we might classify the galaxy as a radio galaxy, since the side view reveals strong emissions at radio wavelengths. But when the jet is aimed almost directly at us, we see a blazar, a galaxy that appears especially bright and variable due to the relativistic beaming of light coming from its jet. These are the most commonly detected gamma-ray sources in the sky by Fermi. Gamma rays, the most energetic form of light, are crucial for astronomers trying to understand high-energy processes in the universe. They offer insight into how particles are accelerated in these extreme environments and how they interact with magnetic fields and surrounding material. Since 2008, Fermi has identified thousands of gamma-ray sources, with blazars making up more than half. Each detection adds to the growing picture of the high-energy universe and the role that AGN play in it. Understanding AGN is more than just studying interesting cosmic phenomena. Many of these active galaxies formed early in the history of the universe. Because of their immense power, they likely played a significant role in shaping their environments, influencing the formation of galaxies and the evolution of cosmic structures. By studying AGN, scientists hope to uncover the mechanisms that helped shape the universe as we know it today. The story of the brightest lights in the cosmos is, in fact, a story about how darkness, supermassive black holes, can generate energy on unimaginable scales, revealing the dynamic and ever-evolving nature of the universe.